Hello everyone and welcome to Sky Scholar. In these 5 videos, I began a review of white dwarf stars, and today I wish to resume these efforts. Astronomers, beginning with Eddington, have advanced that white dwarfs are hyperdense based on their reduced luminosity. They also claim that redshifts measured using selected hydrogen Balmer lines support this conclusion. Unfortunately, the redshifts of metallic lines do not provide any supportive evidence for the claim that white dwarfs are hyperdense. As a result, we now examine what is happening with the metallic lines associated with white dwarfs, and do so by repeatedly presenting citations from the literature. In order to make continued progress for our analysis, let us begin with these spectra from Saumon et al. Obtained for various types of white dwarfs. So far, we have focused on DA white dwarfs such as Sirius B and 40 Iridiani b as represented by the top spectrum. These two stars are the closest white dwarfs to the Earth and have powerful hydrogen Balmer absorption lines with little or no metallic lines evident. DA white dwarfs are also known to possess quasi-hydrogen molecules and quasi-hydrogen molecular cations in their atmospheres, as we learned in the last video. The presence of quasi-hydrogen molecules and quasi-hydrogen molecular cations can act to strengthen the Balmer lines, and such molecules are very likely to be responsible for any hydrogen-based redshifts. Here is a table that summarizes the key features of different types of white dwarfs. The next type of white dwarf has the classification dB. Such stars can possess spectral lines from neutral helium, whereas in the DO dwarf, helium cation lines are present. In both the dB and DO dwarfs, the hydrogen lines are reduced. DC dwarfs are cool stars with no spectroscopic features, whereas DQ dwarfs are rich in carbon, carbon cation, and carbon dimer or C2 molecular lines. DZ dwarfs are rich in metals heavier than carbon. Most DQ and DZ white dwarfs have atmospheres dominated by helium. The most important metal-containing white dwarf is probably Van Maanen 2, the third closest white dwarf to the Earth after Sirius B and 40 Iridiani b. Van Maanen 2 is a DZ8 class of white dwarf, meaning that it is very rich in metals and has a relatively cool temperature. Early on, the metallic lines of Van Maanen 2 caused problems relative to claims that white dwarfs were incredibly dense based on gravitational redshift arguments. For instance, Greenstein measured the wavelength of calcium-2 H and K spectral lines in Van Maanen 2. To his surprise, he noted shifts of the H and K lines which amounted to a velocity difference of 29 plus or minus 7 kilometers per second. That was significant at the 4 sigma level. How can one account for the fact that the calcium-2 lines in this star can indicate dramatically different velocities for the same object? This should be completely impossible, as the calcium-2 H and K lines should have the same velocity shifts. Greenstein also noted the following. The overall mean of H and K is plus 39 plus or minus 4 kilometers per second. The space motion derived by Van de Kamp from the perspective acceleration was plus 160 plus or minus 45 kilometers per second. So the net shift, whatever the cause, is near minus 100 plus or minus 45 kilometers per second. Wow, that is an enormous blue shift for the calcium-2 lines, not a red shift. The lines were also known to be extremely broad, as one can learn in this paper. What a headache for the astronomers and the belief that redshifts indicate ultra-dense objects. What were the shifts of the calcium-2 lines on Van Maanen 2 actually trying to tell us? Now, if you take the time to study white dwarfs, you will find something very strange. For these stars, and as a direct consequence of what had been observed with Van Maanen 2, astronomers advanced that the metal lines found on dwarfs originated from pollution of accreted material or planetesimals onto the dwarf. They speak of metal-polluted white dwarfs, planetary debris, and radiative levitation. In fact, they are so convinced of these concepts that such outlandish ideas are currently accepted throughout astrophysics. Here is a quote. Approximately 30 to 50% of white dwarf stars are thought to have atmospheres polluted with metals. The mechanisms by which this pollution occurs are relatively well understood in the case of cool white dwarfs. The diffusion timescales for metals in these cases can be on the order of days. For hydrogen-rich white dwarfs with effective temperatures, T effective, ranging between 12,000 and 20,000 Kelvin. Therefore, for metals to be observed in the atmosphere, the reservoir of material has to be continually replenished through accretion. However, in the case of hot white dwarfs, temperature effective greater than 20,000 Kelvin, the physics becomes more complex. In this case, the radiative forces in the atmosphere are efficient enough to overcome the gravitational stratification, resulting in metals such as carbon, nitrogen, oxygen, and heavier being present in the photosphere through a process known as radiative levitation. Here is another quote along these lines. Over the past decade or so, the presence of absorption lines from elements heavier than helium in the spectra of single white dwarfs with T effective less than or equal to 25,000 Kelvin has come to be understood, without a doubt, as the result of accretion of disrupted planetesimal from their ancient planetary systems. As a result, our knowledge and understanding of the composition of exoplanets have grown significantly through the extraordinary detail and precision afforded by this powerful observational technique. Imagine, now we are going to learn about exoplanets by studying the metallic lines on white dwarfs. Talk about overreaching. Here is another quote. The presence of heavy elements in these objects is now understood as external accretion of matter from a disk of debris resulting from destruction of a rocky object, asteroid, or small planet by the white dwarf's tidal forces. These objects are thus temporarily imprinted with the chemical composition of the polluting body, providing a unique opportunity to study the chemical composition of extrasolar bodies. Wow! Now metal lines on white dwarfs are going to teach us all about the composition of asteroids and small planets, which in all likelihood never even existed. Here is another great quotation. There is an ever-increasing number of remnant planetary systems discovered around white dwarf stars. The most common observations are metal pollution in the white dwarf's photosphere that is attributed to the accretion of planetesimals that have been tidally disrupted when on star-grazing orbits. This is observed in 25 to 50% of white dwarfs cooler than 25,000 Kelvin, where radiative levitation effects are negligible, so pollution must be external. Observations of the circumstellar environment reveal infrared excess from circumstellar dust in 1.5 to 4% of white dwarfs. What is going on here? Why do the astronomers need to pollute the stars with planet remnants? After all, the metallic lines they speak about are also always found on the main sequence stars. The problem comes from their insistence that white dwarfs are super-dense stars and have enormous surface gravity. Consequently, they cannot explain the presence of metals on these objects, as they should have sunk to the interior of their star through gravitational settling. Astronomers would have preferred not to see any metals on white dwarfs, as it is difficult to account for their presence in an ultra-dense object. Of course, this is true unless they can invent that the material came from beyond the star and had just fallen upon its surface, providing insufficient time for gravitational settling. Since they detect infrared emissions, they also argue that they can see circumstellar dust. They cannot account for such emissions if the stars are gaseous plasma. They need condensed matter, so they have recourse to dust around the star. Yet it is well known that even diamonds can produce emissions in the IR. In fact, this is one of the ways to gauge the quality of gems, as one can see in this figure. Different imperfections in diamonds can give rise to characteristic lines in the IR, and I have advanced that in white dwarfs, a well-defined and perhaps diamond-like lattice is responsible for their reduced emissivity. Such a lattice can also emit in the IR. As a result, astronomers cannot establish that their circumstellar dust even exists. Within their models, such dust is required to help account for the behavior of the metal lines they see. Unfortunately, for those who believe that white dwarfs are incredibly dense, the situation is even worse. Some WA white dwarfs also have metallic lines, as can be seen with the calcium-2K line in this figure taken from Zuckerman et al. The top tracing is for a DA white dwarf. The bottom three are classified as WAZ dwarfs. The Z in this case indicates the presence of metals. As modern telescopes bring more signal-to-noise to the spectrum, the metal lines can currently be seen. How can these metals be there again? What about our enormous surface gravity that is supposed to exist? Heavy atoms like calcium should not be found floating around in a white dwarf atmosphere if the star is truly hyperdense. Therefore, in order to account for their presence, astronomers have recourse to the most peculiar of explanations, anything to keep these elements from being directly associated with an atmosphere in equilibrium with the white dwarf itself. Here's another quote. The atmosphere of white dwarfs usually shows spectral lines of only one element, either hydrogen, spectral type Da, or helium, including spectral type Db. For many years, this has been understood as an effect of gravitational separation in very high gravitational fields in these objects. Elements heavier than helium are observed in a few objects at high temperature, above 25,000 Kelvin, where some elements can be supported in the atmosphere against gravitational forces by selective radiation pressure. See Chayer, Fountain, and Weidemann 1995 for a detailed discussion. At temperatures below 20,000 Kelvin, some white dwarfs also show traces of heavy elements, although the timescales from gravitational diffusion are short compared to evolutionary timescales, i.e., the heavy elements cannot be primordial, and radiative levitation is negligible. The most widely accepted explanation for these elements is accretion during passage of the star through an interstellar region of relatively high density, followed by subsequent downward diffusion. Do you see what is happening? Astronomers keep the heavy elements from gravitationally settling by using radiation to keep the metals suspended when the star is hot. When the dwarf is cooler, they have to invoke pollution from outside the dwarf and insufficient time to settle the newly accreted material. The only thing required is the suspension of disbelief by the person who is reading such writings. The reference by Chayer et al. Is actually a classic. The authors justify radiative levitation for carbon, nitrogen, oxygen, neon, sodium, magnesium, aluminum, silicon, sulfur, argon, calcium, and iron, all from theory, of course. Here is a quotation from that paper. Finally, we compute the selective radiative acceleration transmitted to a given element through bound-bound absorption only. This follows from the demonstration presented by Michaud et al., which showed that photoionization processes contribute generally much less than bound-bound transitions to the transfer of momentum from the radiation field to a levitating atom. In the first place, if radiation strikes an atom, it needs to be ionized first and the electrons ejected. In fact, that was the argument astronomers made to account for the helium-2 lines in the chromosphere of the Sun, as we discussed in this video. Do you recall how it was postulated that helium was conveniently ionized by coronal photons? Now, in the white dwarf, astronomers argue that such ionization is not favored for their process, but rather that the atom undergoes bound-bound transitions preferentially, such that its altitude can be increased. Talk about reaching for the stars. In reality, we see calcium-2 on white dwarfs, the same elemental species seen on our own sun. Zuckerman et al. Speak of seeing lines from calcium-2, iron-1, magnesium-1, and aluminum-1 exactly also as seen on the sun. Next, what about the accretion idea? With this approach, the star has to pick up elements in a dense cloud. They justify this claim by writing, thus, we were surprised to see interstellar lines towards GD31, LHS 1549, and G140-2. Calcium-2 and magnesium-1 seen towards these stars are evidently interstellar because the line radial velocity differ greatly from the hydrogen beta line velocity. We are back to redshift arguments. Do you see how the elements must be evidently interstellar because their redshifts do not agree with those from the hydrogen beta line on the dwarf? So if the astronomers do not like the redshift observed, they simply move the element off the dwarf. The incorrect redshift problem is thereby solved, and astrophysics gets to keep their unrealistic densities. The authors of the paper continue. It is possible that one or more of the calcium lines listed in Table 1 are interstellar rather than circumstellar. However, this will not be the case for many, if any, stars for the following reason. First, the hydrogen beta and calcium 2 velocities agree to within our measurement uncertainties. Second, in many cases, these velocities are outside of the range of local interstellar velocities. And third, many K-line equivalent widths are much too large to be plausibly due to interstellar gas. Note how they have moved the position of the calcium-2 lines out of the dwarf atmosphere into a circumstellar cloud surrounding the white dwarf. Astronomers give the calcium-2 line the same velocity as the dwarf and the computed velocity for the hydrogen beta line. But if the calcium-2 line really originated from a circumstellar cloud, the redshift one associates with its velocity must not agree with the redshift for hydrogen beta associated with gravity. As a result, one must separate a redshift associated with star velocity from the gravitational redshift of the hydrogen line itself. After all, the hydrogen beta line is supposed to be gravitationally shifted because it is part of the dwarf's proximal atmosphere. In any case, the assumed high gravity of the dwarf must not cause calcium gravitational settling because the metal is clearly seen. So they must just keep the calcium-2 far away from the surface in a cloud and all is well. The third point of this quote is also noteworthy. The calcium-2 lines are very broad, and this once again can indicate a Stark shift mechanism on the star. Stark shifts could be affecting calcium-2 and hydrogen beta in a similar manner, so the shifts indicate nothing relative to gravity. So in this context, let us return to the paper by Preval et al. In their paper, they display many unusual shifts and hasten to move the metallic lines off the surface of the white dwarf. Simply examine their figure 14. The solid line represents the spectrum obtained, and the dashed red lines are the Gaussian fits for 3 peaks which they claim are all associated with silicon-3. They report associated velocities of minus 32.8 plus or minus 0.4, 12.8 plus or minus 1.3, and 24.4 plus or minus 0.3 kilometers per second. So in the same circumstellar cloud, we have both positive and negative velocities now. Next, examine their figure 16 associated with the same star. We have 3 more lines, but this time they are said to be associated with silicon-4 with velocities of 16.1 plus or minus 1.4, 25.3 plus or minus 0.4, and 80.6 plus or minus 0.2 kilometers per second. The first 2 are said to be circumstellar, but they assign the 80.6 kilometer per second line to the photosphere as it fits their preconceived notions of what that shift represents. No mention of radiative levitation in this case, yet the white dwarf WD 0455-282 is said to be incredibly hot at about 65,400 Kelvin, well above the 25,000 claim necessary for radiative levitation to take place. They also note in the abstract, we compared the measured photospheric abundances with those predicted by radiative levitation theory and found that the observed silicon abundances in all 3 white dwarfs and the observed iron abundances in WD 0621-376 and WD 2211-495 were larger than those predicted by an order of magnitude. These findings imply not only an external origin for the metals, but also ongoing accretion, as the metals, not supported by radiative levitation, would sink on extremely short timescales. Talk about unreasonable. In this instance, they discount radiative levitation even though the WD 0455-282 white dwarf has a temperature well in excess of what is claimed to be needed for radiative levitation. At the same time, for the same star, a total of 6 separate velocities are reported for silicon ions, ranging from minus 32.8 to 80.6 kilometers per second, but with no smearing of the lines as one might expect in a cloud with a wide range of velocities. The problem, of course, is that one cannot have multiple shifts if the lines all originate from the atmosphere of the white dwarf, and if the dwarf is supposed to shift the lines to the same extent using gravity. Therefore, the metals are moved to circumstellar disks, which become endowed with widely varying velocities. This is a sure sign that all the shifts associated with white dwarfs have absolutely nothing to do with surface gravity. Rather, we are dealing with velocity of the star itself and start shifts produced by chemical processes in the atmosphere of the dwarf. It is simply unreasonable to remove all true scientific meaning of metallic line shifts by selectively moving the lines away from the dwarf into interstellar space and circumstellar clouds, or by invoking radiative levitation as another degree of freedom only when suitable, or placing the line on the photosphere when we like the redshift it produced. This video has reviewed yet another proof that white dwarf stars are not incredibly dense. The presence of metals on the surface of the dwarfs implies two things. First, these stars are not ultra-dense. Second, all our claimed gravitational redshift calculations are ill-founded. What makes the most sense? Should we allow reasonable densities and naturally occurring metals in the atmosphere of the dwarf? Or should we permit recourse to incredible densities and the use of pollution, accretion, planetary debris, and radiative levitation? Astronomy dismisses the evidence in order to accept the fanciful. Well, that is all for today. We will return to the white dwarf in the next presentation. So if you enjoyed the video, promote the channel, mention the videos to your friends and to your local astronomy club, support me with a like, and subscribe for more videos as we look more closely at the sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on the next video.